4, radical and rational functions review. We're just staying with just this piece today. So again, this is kind of, again, review for you guys is the bold is the concept that's like a curriculum standard you should do. The how-to kind of refreshes how to do it, and then we have an example of doing it. Okay, so that's, if you're wondering what all that stuff is, that's what it's saying. It kind of looks repetitive when you're reading through it, but the standard is sketch a graph of y equals radical f of x given the graph of y equals f of x. So sketching a radical function. Okay, so remember the points on y equals f of x where the y coordinate 0 and 1 also lie on the graph of the radical function. That's the invariant point. So we talked about when your output of your regular function is a 0 or a 1, that is going to be the same exact value for your radical function because the square root of 0 is 0, the square root of 1 is 1. We call those invariant. We've talked about that multiple times. Determine the square roots of the y coordinates of the other points, and then we go from there. So given the graph of f of x, sketch the graph of radical f of x. State the rules and sketch the domain and range for both. Okay, so they give us the original. We're going to sketch the radical graph. So again, this is what's really important. What's really important is we need to mark the invariant points now. This is invariant. That's invariant. This is invariant. This is invariant. That's 0 and 1. So remember, the radical graphs, okay, when you're between 0 and 1, they are above the f of x because it's a bigger number because when you square root a fraction of 1/2, it gets you a bigger number than 1/2. Okay, so it goes like this. Just show that it's outside. I'm exaggerating. It's probably not that much. And then right here is at 4, so I know this is going to cross at what? 2. So I know it's going to kind of come pretty flat here, like this. And then it's going to hit, and it's going to come out again, and then just kind of curve back onto the top there. So that's what your graph is going to look like when you sketch it with your invariant points. What's that? They could. They could. Yeah. I don't know if they do much sketching. I'm still reading through the exemplars, but I think they're more for the written. Just kind of looks like it's going to be a log question to me because they're going through the steps, like change the exponential and solve for x. Like, and they're going to make you just do that. But we'll get to that later. Okay. But anyway, I don't think they'd make you graph though, Cash. That's really hard because it's subjective and then scaling, and there's a lot of different things that can make that difficult. Okay, so but the point is invariant points. Invariant point's a really good numerical question, right? So it's like, where's your invariant point for 1? Okay, well, my numerical point for 1 is at 4, right? Or -4. Okay, so state the domain and range for both graphs. So f of x. F of x has a domain of what? Yeah, the original. Yep, so -4 to 4. And the range, greater than 0, less than 4. Yeah, so exact domain for the other one is going to be basically the same. So we'll just call it just root f of x. So the range, let's do the range first because it's easier. The range is going to be 0 to 2. Like that. But the thing is if you're talking about the domain, well, this is my question to you. By putting a radical on there, from the picture, does that affect what we can plug in? So what I mean is, well, let me take a step back. This one doesn't have one, but what values do we have to avoid when we're doing range of radical f of x? Negatives. Is there any negative y values in this picture? So there's nothing we're avoiding, so they have the same domain. there's nothing that we're avoiding. So if this picture, if I just drew one just for an example, if I told you to draw the radical graph, like if this is f of x, a new one, if I said it was this, your domain now is here to here. We cannot be down here at all. So you would avoid that section. The picture that I have for you here, all of this is in the positive, so the domains are the same. The whole thing's okay. It's just 4 to 4, negative 4 to negative 4. Same. Okay, does that make sense? Okay, so again, remember, radical functions, we're avoiding negative outputs. Because if you have a negative output, that's in the radical now. Okay, good. All right, let's keep on going. Good questions. Okay, so solve the radical equation graphically. Okay, so that's a standard. How to determine the roots of a radical equation using the zero method or the intersect method. So remember, intersect method, that's y1, y2. See where they cross. Okay. You can do that. I'm going to go and do the zero method. So these are actually both calculator. So let's just bring up the calculator and do it real quick. Actually, I'm just going to graph it myself. You guys can put on your calculator if you want. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. And then 2x plus 1 is negative 1/2. So it'll be right there. If I put 0 in, I get 1. Okay. And so this thing goes like this. And this thing goes like this. So it has intersection kind of a little bit more left than that, but your picture's going to be close to that. And they're saying it happens at 9.5. I'm going to go ahead and do it on my calculator now. I just want to sketch it roughly, just kind of get an idea. But we're finding, this is solve. So when it's solve, you're just finding the actual solution where they cross. Okay, let me go ahead and go check this out. Let's put this up here. Let me bring my calculator. It's on the other page. Hold on. And I think intersect's easier. 0, you have to move them over. There's more room for error. Okay, so I'm just going to put it in here. So we got radical second square root 2x plus 1. And the next one is simply x minus 5. What's my window right now? My window's good. I don't need that big of a min. Let's go ahead and make my min just -10. Just go standard. Okay, and graph. Okay, so we can see it there, right there. So it's just second, trace, intersect. Intersect, just hit enter 3 times. It should be fine. Enter, enter, enter. Yeah, 9.46, so 9.5 is the solution. Remember, you're solving for x. Okay, you're solving for x. Okay. It says nearest tenth. Okay, to notice in your final clip, you guys need to make sure you're paying attention to your rounding. Okay, you guys rounded the wrong tenth. It's going to be wrong next Wednesday. Okay. All right. Next one, same thing. So I'll just go ahead and stay at the calculator here. It's saying solve the rational graphically. So we have left side equals right side. So this one, make sure you use brackets with these, okay? So make sure you go bracket 2x squared plus 3x minus 1. Close the bracket. Now do your dividing bar. Another bracket, x minus 1 on the bottom. Okay, I'm going to clear the second one. And then we have bracket 4x plus 5 divided by x squared plus 3. Okay, so there it is. I'm not sure if my window's going to be good or not. Okay, it looks like it is. Okay, so what do you see here? There's 2 intersects. You have 2 solutions. Okay, good job. This is probably good enough. You could zoom in a little bit more if you wanted. You could cut like these off. Maybe I'd go to 5, 5, -5, okay, if I wanted. But you should be fine here. But there's 2, and using intersect, you do need to get close to it so it goes to the correct one. So if I do second trace intersect, and I just hit enter 3 times, so it's giving me that second one actually. It's over here. So first answer, -0.252. Nearest tenth, so -0.3. Okay, do it again. and I want to make sure I get closer to where I want to go. So I'm going to move it down here. I'm going to hit enter, 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 and I get the second one for negative 2.1. So negative 0.3, negative 2.1. Okay. Questions? Pretty straightforward that, right? All right, then we're going to review asymptotes and point discontinuity. Okay. So again, for these, I'll just write the answers right here. We got x equals negative 0.3 and negative 2.1. Okay. All right, third page, last page. Okay, so determine non-permissible values of rational functions. So again, vertical asymptotes. Where the function's undefined, there's a value of x that makes the denominator equal to 0. Okay, so that's very simple. When your denominator makes, it gets a number that makes the denominator 0 is a vertical asymptote, unless it cancels. Okay, if it cancels a point discontinuity, either way it's still an undefined value. Okay. Horizontal asymptotes, degree on the top. So remember, there's three cases for horizontal asymptotes. If your top's bigger, what's that mean? If your top's growing faster. Nope, top growing faster. None. If your top's growing faster, there's no horizontal asymptote. Okay? Degree on top is greater than degree on bottom, no horizontal asymptote. Degree on top is less than, okay, like so the top's like 2 over x, that's the 0. And then remember, if they're the same coefficient or same degree, the coefficients over each other. X squared and x squared, if it's 5x squared over 3x squared, your asymptote's 5 over 3. Okay, so that's your horizontal asymptote cases. Okay, point discontinuity, again, you need to factor, have them in factored form to see these, and they're when factors cancel. When their factors cancel, that point has a hole. Okay, to find that hole, you plug in the value that it would be after they cancel to see where it's at. Okay, that's what you do. So let's go ahead and do one here. So let's do this example. All right, so first off, term domain and range. Okay, so you get the domain and range from those things. So first off, I want to see if I can factor the top here. The factoring of the top is x minus 1, x minus 4. So I do see I obviously have a point of discontinuity, not a vertical asymptote. Okay. All right, so what's growing faster? Top, bottom, or the same? Top. So there's no horizontal asymptote. None. Is there a vertical asymptote? There's not a vertical asymptote per se. There's going to be a point, right? So there's no actual asymptote. Okay, this cancels. So we know the point of discontinuity, POD, is 4 something. To figure out that y value, we plug in after the cancel. So just x minus 1. So what's 4 minus 1? 3. So your point of discontinuity is 4, 3. Okay? I'm going to quickly sketch this, and we'll talk about domain and range. This graph is actually quite simple. It looks like this. Except for at 4, 3 here, it's an open dot. Okay? So the domain of this and the range of this. What's the domain? Yeah, x can't be 4 is all. X can't be 4, everything else is fine. So x can't be 4, all reals. The range, y can't be 3. Okay? That's everything. All right, we'll stop there for today.